So in this video we're going to look at how to identify the t intervals over which a parametrically defined curve is concave up or concave down. And the key idea from Calc 1 that we want to remember is that when we get a change in concavity, that's typically going to occur at an inflection point on the curve. So here I have a change from concave down to concave up, and this inflection point is going to happen usually when the second derivative is equal to 0. It can also happen when the second derivative is undefined, so we need to be careful about checking for undefined second derivatives as well. The idea behind the inflection point is that's the point at which the directionality of the tangent line rotation changes. So for example, as you sweep across this curve, if you draw in a few sample tangent lines to the curve before you get to the inflection point, here they have slopes that are positive. The slope goes through 0, and now I have a negative slope of the tangent line. So the tangent line is changing from positive to negative. So there's a sense in which we can say that the tangent lines are rotating in a clockwise direction as they sweep along the curve. Once we get through the tangent, the inflection point where the second derivative is 0, we can see that I have negative slope, a slope of 0, positive slope. The slopes of the tangent lines are changing from negative, moving through 0 and becoming positive. So they're rotating in the counterclockwise direction as we move along the curve. So the inflection point is the point at which that direction of rotation changes. And it's changing in this case because when the second derivative goes to 0, it allows for a change in the rate of change of the tangent lines from a negative rate of change to a positive rate of change, or vice versa. So the key from Calc 1 is to find test intervals for concavity. You take and find the second derivative. You determine when the second derivative is equal to 0. If the second derivative is undefined somewhere, you want to include that number in your evaluation because it could potentially be a boundary where concavity changes. So to get the second derivative, we first need to calculate the first derivative, dy dx, and we know that we calculate that by doing d dt of the parametrically defined y, and y is parametrically defined as t cubed minus t. And then we divide that by d dt, the derivative with respect to the parameter of x, x of t, which is just 3t squared. So when we take the derivative of the numerator, we're going to wind up with 3t squared minus 1 over a 6t. And then we need to calculate the second derivative, dy2 over dx2, or y double prime if you want to think about it that way instead. This should be, that 2 should be tucked in right there to denote that we're taking the second derivative. So to get the second derivative, we just simply take the derivative with respect to the parameter of dy dx, or y prime. Take ddt of dy dx. And then we take d dt of the parameterized x again, so that's just 3t squared equals. And what I want to look at, or what I want to realize, is I need to take the derivative of dy dx, and right now dy dx, in the form it is, I would need to use the quotient rule to take the derivative of this. So it might be convenient for me to break it into the two individual fractions, 3t squared over 6t minus 1 over 6t, which is equal to 1/2 of t minus 1/6 of a t to the negative first, as long as t isn't equal to 0. The other thing I want to look at and identify is what is the domain for t to begin with? What's the overall domain for t? When we look at x and y, we can see that x is defined for all t. There's no square roots to worry about, no possible divisions by 0. And y is the same way. Y is equal to a third degree polynomial, so there's no domain restrictions. So we know t is allowed to run over the interval from negative infinity to infinity. And then we're looking for places where the second derivative is going to require us to break it into some test intervals. So as long as t isn't equal to 0, this is the sticky point. I can simplify the derivative into this form. So I can take d dt of 1/2 t minus 1/6 t to the negative first power. And then the derivative of 3t squared is going to be 6t again. And the derivative of the numerator is going to be 1/2 minus the negative 1 will come down and make that a plus. So I get plus 1/6 of t to the negative second power all over 6t. So right now I'm noticing that the second derivative as well as the first derivative, they're both undefined when t is equal to 0. So because it's undefined when t is equal to 0, I'm going to include t equal to 0 in my establishment of the test intervals. And then we want to check to see, is it, does the second derivative, question mark, does it equal 0? And to figure that out, the only way the second derivative can equal 0 is if the numerator of the second derivative is equal to 0. So we simply set 1/2 plus 1/6 t to the negative second power. We set it equal to 0. And we're going to run into a problem right away, because when I subtract 1/2 from both sides, and I have my, so over here on this side I have 1 over 6t squared equaling now I've got negative 1/2, and if I multiply both sides by negative 2t squared, I'm going to wind up with negative 1/3 equaling t squared. And to solve this, I would need to take the square root of both sides, and I'd get plus or minus, but this is going to be a complex result, and t runs over the real numbers from negative infinity to infinity. So because I get a complex result, when I try to set my second derivative equal to 0, I don't have to worry about any additional t values. So I'm going to set up my test intervals using the t value for which my second and even my first derivative was equal to 0. So my test intervals are going to be from negative infinity up to the bad spot. And then my second test interval is going to be from that bad spot where the second derivative was undefined, running out to infinity. And to do the test, we'll just run the second derivative test. We'll say pick any t value on this interval. T equal to negative 1 is convenient, and plug that into the second derivative and see if the second derivative is positive or negative. If the second derivative is positive, my interval is concave up, and if my second derivative is negative, my interval is concave down. If it's equal to 0, then I have an inconclusive test, and I wind up having to try something different. So plugging negative 1 into the second derivative, I get 1/2 plus 1/6, and I'm going to have a negative 1 squared in the denominator. I'm moving this guy down, and so I can change the sign on the exponent, right? 1/6 t to the negative 2 is the same as 1 over 6t squared. So doing that, I plug this in, and I don't even need to, I do need to get the denominator, so it's going to be 6 times negative 1. And I don't need to evaluate the number. I need to know if it's positive or negative. And by looking at it right here, I know that it is less than 0. The negative 1 being squared is going to make this positive. So I have a positive numerator. I'm going to have a negative denominator. And a positive divided by a negative is negative. So this ratio is less than 0, which means my graph is concave down on the interval from negative infinity to 0, and I run the same test here. Pick any number in this interval. I'm going to pick t equal to 1. Plug that 1 into the second derivative. I get 1/2 plus 1 over 6 times 1 squared divided by 6 times 1. And without evaluating this number, we see we have a positive numerator, a positive denominator. This is greater than 0. It's a positive number, which means I'm concave up on the interval from 0 to infinity.